In this lecture, we're going to go over heat exchangers. Heat exchangers have many applications. We have direct heat exchangers such as a mixing chamber, where our hot and cold streams physically touch. And you have an indirect heat exchanger where your hot and cold streams physically do not touch. Heat exchangers can have multiple inlets and outlets. For a control volume consisting of a heat exchanger, the only work is flow work. So the work for our control volume is equal to 0. Also, typically, changes in kinetic and potential energies of the flowing streams can usually be ignored. So our energy equation reduces down to our heat transfer plus the sum of what comes in minus the sum of our enthalpy out. Typically, heat transfer only occurs within a heat exchanger, so the heat transfer with the surroundings is often 0, so our energy balance further reduces down to 0 is equal to the sum of the mass flow rate times the enthalpy in minus the mass flow rate times the enthalpy out. So we're going to look at 2 examples. First, we have steam entering a condenser of a vapor power plant at 0.1 bar with a quality of 0.95, and condensate exits at 0.1 bar and 45 degrees Celsius. Cooling water enters the condenser in separate streams as a liquid at 20 degrees Celsius and exits at a liquid at 35 degrees Celsius with no changes in pressure. Heat transfer from the outside of the condenser and changes in kinetic and potential energies of the flow streams can be ignored. For steady state operation, we want to determine the ratio of the mass flow rate of the cooling water to the mass flow rate of the condensing stream, and the energy transfer from the condensing stream to the cooling water in kilojoules per kilogram of steam passing through the condenser. So the first thing we have is our mass balance. From our picture here, we have the mass flow rate of 1 is equal to the mass flow rate of 2, and we have the mass flow rate of 3 is equal to the mass flow rate of 4, since these 2 streams remain separate. The ratio of cooling water to the condensing stream the mass flow rate 3 divided by the mass flow rate of 1. How are we going to find these mass flow rates? Well, let's do an energy balance. We have 0 is equal to mass flow rate 1 times H1 minus H2 plus mass flow rate 3 times H3 minus H4. So the mass flow rate of 3 over the mass flow rate of 1 is equal to H1 minus H2 over H4 minus H3. So state 1, P is equal to 0.1 bar, and our quality is equal to 0.95. So we have a 2-phase. We get H1 is equal to 191.83 plus 0.95 times 2584.7 minus 191.83 equals to 2465.1. And state 2 is condensate, which is a liquid. So we're going to assume H is approximately HF, which is equal to 188.45. The same is true for H3 and H4 since they are liquid. So we have our ratios of our mass flow rates are equal to minus 188.5. Our ratio of our mass flow rates is 36.3. So we have to calculate the heat transfer rate from the condensate stream to the cooling water per kilogram of steam. So I'm only going to look at the steam side. Since I'm only looking at the steam side, there is heat transfer. There's still no work. There's still no kinetic or potential energies. So my Q per unit mass is equal to H2 minus H1. So our heat transfer per unit mass of steam is minus 2,276.7 kilojoules per kilogram, and again it's negative because it is leaving the steam and entering the cooling water. We're going to do another example of a mixing chamber. So we have an open feed water heater operating at steady state with liquid water entering at one inlet at 10 bar and 50 degrees Celsius. A separate stream enters at inlet 2 at 10 bar and 200 degrees Celsius with a mass flow of 16 kilograms per second. And we have saturated liquid at 10 bar exiting. Ignoring heat transfer with the surroundings and neglecting kinetic and potential energy effects, we want to determine the mass flow rate at inlet 1. So what we have is P1 is equal to 10 bar, T1 is equal to 50 degrees Celsius, P2 is equal to 10 bar, T2 is equal to 200 degrees Celsius, the mass flow rate is equal to 16. We have saturated liquid, and P3 is equal to 10 bar at our exit. So in, out. So we start with our mass balance. We have mass flow rate 1 plus mass flow rate 2 is equal to mass flow rate 3. So what comes in has to equal what goes out. I'll do my energy balance. There's no changes in kinetic or potential energy, there's no work, and there's no heat transfer. So I have mass flow rate 1 times enthalpy 1 plus mass flow rate 2 times enthalpy 2 minus mass flow rate 3 times enthalpy 3 is equal to 0. We're going to use the fact that mass flow rate 3 is equal to mass flow rate 1 plus mass flow rate 2 to eliminate it from our equation. We're going to have 0 is equal to mass flow rate 1 times the enthalpy of 1 plus mass flow rate 2 enthalpy of 2 minus mass flow rate 1 plus mass flow rate 2 times the enthalpy at 3. So I'm going to solve for my mass flow rate of 1. And my mass flow rate at inlet 1 is equal to my mass flow rate at inlet 2 times H2 minus H3 over H3 minus H1. So for state 1, we had liquid water. So H is approximately HF, which is 209.33 at 50 degrees Celsius. State 2, we have P is equal to 10 and T is equal to 200. My temperature is greater than my saturation temperature, so it's superheated. And for state 3, we have saturated liquid. So if we plug numbers into our equation for our mass flow rate, we're going to have 16 kilograms per second times 2827.9 minus 762.81 over 762.81 minus 209.33. We get our mass flow rate at state 1 is equal to 59.7 kilograms per second. In our next lecture, we're going to go over throttling devices.